All right, welcome everybody to our February installment of the PacTrans webinar series. My name is Cole Kopka. I'm the Assistant Director of PacTrans, and we're really excited today to, we've asked a few of our PIs who have done a number of PacTrans funded research projects together to come on and share about some of their recently completed work titled Developing Design Guidelines for Commercial Vehicle Envelopes on Urban Streets. Before I introduce today's speakers, I just wanted to give you some of the logistical rundown of kind of how you can interact with us on Zoom today. So we have 3 features available to you. The first is a raise hand option. So after our presenters are done presenting and we open it up for some Q&A time, if you'd like to verbally ask your question, you can raise your hand, and then we can allow you to speak so that if you choose, you can ask a question verbally. The chat box is the only people you can communicate with in the chat box is the panelists. So if you have a comment or if you're having a technical difficulty, you can reach out to us using the chat box. I would ask you to keep all of your questions to the Q&A panel. So at the bottom of your screen, you'll see a Q&A icon. You can click that, it'll open up the box. You can leave your questions in there throughout the presentation and we will get to them at the end. If you see a question you like, you can upvote it by hitting like on it and it will prioritize in the order. It'll auto sort based on what people have liked the most so that we know which questions the most of you want to hear from. Especially if we end up with a lot of questions that we won't be able to get to in the hour. So, and with that, I'm going to introduce today's speakers. So our first presenter is Ed McCormack. He's a research associate professor in civil and environmental engineering at the University of Washington, and he is the director of the Online Masters of Sustainable Transportation program here at the UW as well. And then our second presenter is Hisham Jashami, who is a research associate in civil and environmental engineering at Michigan State University. And when he was participating in this PacTrans funded work, he was a PhD student at the Oregon State University. I'm gonna now turn it over to Ed and he can get started.
Okay, thank you. Let me share my screen. There we go. All right. Hopefully you can see my title slide. So we're going to be talking about envelope, which is the space that you need around a vehicle to unload freight on an urban street. This project was as a lot of these research projects, there's a number of us that worked on it. In addition to myself and Hisham and Goodchild and David Hurwitz were co-PIs along with me, and we had a couple great students, Douglas Cobb and Manali Seth, that worked on this. And I also want to thank PacTrans for the support of this research project. This is sort of one of 3 linked research projects we've got PacTrans funding for, so we've almost have a research program going here that we've done with OSU. So sort of an overview of what we're going to talk about is I'm going to go over why we actually need to understand commercial vehicle load zones or envelopes around vehicles. I'm going to show you some examples of some problems which kind of prompted us to do this research and talk about kind of the research needs. Mainly, there's a lot more freight moving out there due to e-commerce, and so there's a lot more demand for load and unload zones in urban streets. And there's not much design support. And I'm going to talk about how we collected data by direct observation simulated deliveries. And I'm going to pass it along to Hisham, and he's going to talk about where we took the data from the first part of the project and put it into a driving simulator. And he's going to talk about findings and how we applied the findings. So if you're a planner or an engineer and somebody asks you to go out and put in a parking zone for a handicap van, you have some pretty great guidance where to go. You know you're going to need 8 feet, a buffer, sort of 8 feet alongside the van for the wheelchair ramp and for the wheelchair user to come out and spin around and get going the direction they want to go. So it's pretty clear cut. Now, if you're that same planner and engineer and somebody asks you to go design space for a commercial vehicle load zone. There is very little information out there. And, as I work in an urban freight lab at UW, and one of the things we do is we go out and look at freight being loaded and unloaded. And it's pretty clear, as you can see by these pictures, that there's not really great facilities for trucks to load and unload. And there's all sorts of problems. Like here is an example of some driver that made his own load zone by putting out traffic cones, and that kind of works, but it gets in the other people's way. Or, here's another example of where lift gates coming off the back of a truck, and there's not enough space for the guy to unload his goods. And so he's blocking the crosswalk and forcing the pedestrians to walk out in the street, which is not good for the pedestrian. Or, here's a truck that's longer than the load zone. So you notice he's parking in a turn lane here. So this courier has to walk out in the street to get that hand truck full of goods off to the curb where he needs to, finish off his delivery. Or, here's a driver actually walking in the roadway, which is not particularly safe for the driver. He has a hand truck and he's out there in the traffic lane. Again, not a great situation. Or here's a load zone that's just too short, so the driver has to extend his ramp off into the sidewalk, which again could have conflicts with pedestrians. And so, there's a lot of pressure for curb use in cities. So the cities are starting to give quite a bit of consideration to the allocation of curb space, and there's a lot of people that want that curb space. Not only is there, the freight folks, there's the Uber and Lyft folks who want to use it to drop off people. Transit wants bus stops. Taxi folks want it. People want to park to go shopping. And there's just pressure on curb space, and it's gotten a lot worse with the rapid growth of e-commerce. Even pre-COVID, e-commerce was growing. It went from 2% of all retail activities e-commerce a few years ago to about 14 to 15% recently. And there's some estimates that e-commerce has grown due to COVID by it's extended the growth rate or reduced the growth rate of e-commerce by 5 years. So, everybody wants curb space to unload and load goods. And there's also issues with the drivers being killed and injured making deliveries because of improper load infrastructure. We looked for statistics for the United States. We couldn't find them, but we did find some statistics in Britain that showed that every year some delivery drivers are killed as they're delivering and loading and unloading from their trucks. So what happens is the existing road infrastructure doesn't really accommodate the needs of delivery trucks. So a lot of ad hoc solutions prevail. So drivers often block roadways and pathways. I mean, you can see in this picture here, the green path is a bike path. And so this driver has forced a car to drive in the bike path and get in the way of bicyclists. So there's a lot of what we call unauthorized behavior where the drivers are parking in bike lanes, on sidewalks, blocking turn lanes, parking in the middle of the street, all sorts of things that just don't work very well. So the other thing is, as I mentioned up front, is that, if you're putting in a disabled parking spot, there's lots of great information in roadway design and standards guides, but there isn't much in anything the same design guides for commercial vehicle load zones. So there's really significant gaps concerning freight and street design prescriptions. Also, like if you go into complete streets and smart growth and you look at kind of their prescriptions there's very little accommodation for dealing with trucks. I mean, they deal with all sorts of other modes, but they don't talk about that freight activity, which is critical for a vital urban area. They just don't typically account for it. So the research need that this project addresses is that commercial vehicles using load zones aren't really provided with a usable or consistent envelope, and that's the space around the vehicle to do unloading and loading activities. And so the goal of the research project was to explore where commercial vehicle activity disrupts pedestrians, bicyclists, and motorists. We focused mainly on bicyclists. And the whole idea is that this information would support better roadway and loading zone design guidelines. Ultimately, we'd love to find this information in something like the manually uniform traffic control devices or smart growth prescriptions. That would be great. And again, here's a picture of a driver that's walking in the bike lane, which, he gets hit by a bicyclist. Not good for the driver, and it's not good for the bicyclist. Okay, so the way we approach this research is we had it kind of two steps. I'm talking about the first step, and Hisham's going to talk about the second step. First step is we did an observation of current practices and evaluation of sort of required infrastructure. And then we simulated that roadway user behavior in a bicycle simulator. So we and it started out with observation of current practice, and we went out and looked at 25 deliveries in various parts of urban Seattle. And the point of this was just to sort of observe how the mechanics of urban delivery occurred. And so what we did is we would go out, we looked at the type of truck, box truck, a big truck. And we were particularly interested in the door location. Is it on the side of the truck? Is it on the back of the truck? Does the door roll up? Does it swing out? Because those all have different impacts on the envelope around the truck. We looked at the driver behavior in the past. Where did the driver walk? Did he walk around the front of the truck, side of the truck, and around the back, that kind of thing? And we looked at the accessories that the driver used to move the goods around, ramps out of the back of the truck, hand trucks like you see there in the picture, pallet jacks for bigger loads, and kind of whatever other things they used, bins or other loading accessories. We looked at what was being loaded and unloaded, and we looked at the environment where these activities were occurring. So this kind of gave us a picture of how loading activities occurred. And we kind of quantified the findings, and so we noticed that many vehicles had swing out doors as opposed to roll up, which is relevant because the swing out door takes up more room. And no surprise, most drivers walked on the back of the vehicle and on the passenger side of the vehicle, which surprised us a little bit. So they actually came around the front of the truck and walked down the passenger side. Lots of drivers used hand trucks, or some of them just carried the package in their hand, or they used pallet jacks. And 43% of the drivers unloaded out of the back. So that gave us kind of sort of the parameters of the load and unload process. And we wanted to measure that envelope while these drivers were doing this activity. And so we originally thought, or we briefly thought, well, we'll just go out and find drivers on the street doing these load and unload activities, kind of measure how much space they took. But we realized that that was not very safe. The drivers in a hurry, it just didn't work very well. So we simulated urban deliveries in a controlled environment. And this is where we got our measurements in the envelope. And so we went to three different companies that we had some relationship with, and they allowed us to go into their warehouse or out in their parking lot and do simulated deliveries. We had their drivers, carry fake packages. So we used UW Moving Services, which is close to our office, which is handy. United Parcel Service, we went down to one of their warehouses and they provided a number of trucks. And then a restaurant supply company called Charlie's Produce, which brings fresh food to restaurants. So what we did is we initially measured the closed vehicle footprint. So that's with all the doors closed. So basically it's kind of the size of the freight vehicle. And then we measured the open vehicle footprint. So that's with the doors open, the lift gates out or the ramps out. And that kind of gave us the space the truck required without any activity. And then we measured the active vehicle footprint. And that's where we measured basically the path of the driver and the path of the freight coming in off the truck. And then since we had experienced drivers, we also interviewed the drivers and talked to them about the loading and unloading process, just so we had a better idea what they might need. So here we are. What we did is we had students out with chalk, and we would have a driver load something in the truck and unload something in the truck. We would mark where the hand truck went, where the driver went, and where the pallets went. For example, here's a load of empty boxes, but it'd be like a load of bananas being loaded and unloaded on a truck by Charlie's Produce. So for each one of the delivery activities, we had a pretty intricate diagram here, which we recorded the driver's positions, recorded and measured, and recorded the location, the accessories, the hand trucks and things like that, how far out from the truck the accessories typically went, and the turning radius of the accessories, particularly the wheeled accessories. So here's just some example measurements. The maximum width of the trucks we found was just a little under 10 feet with mirrors. It turns out mirrors, stick out beyond the truck and they take additional space. A typical swing out door requires a little more than 3 feet. And those lift gates, like you see in the Coca-Cola truck down here, actually take a lot of space behind of a truck. They need almost, a little more than 15 feet behind the truck. So the driver needs that much space beyond the back of his truck in order to do his load unload activities. There's a few things that caught us a little bit by surprise. Now we knew we could measure a ramp, it sticks out the back of the truck by 13 feet, but we didn't realize that you need, additional 6 feet so that driver can deaccelerate coming down the ramp and get that hand truck turned around. So, that had added some additional space in the back of a truck that a driver needed to load and unload. So, this let us estimate kind of the appropriate commercial vehicle envelope to reduce conflicts of other road users. And the envelope, we had these measurements for different vehicle types and different handling equipment, different hand trucks, pallet jacks, and cargo characteristics. So let me show you an example of the findings. So what could do is you take the size of the truck, which is the open vehicle footprint, plus the active vehicle footprint. So that's the space needed for the drawers. And then, the active vehicle footprint, that's the space the driver needs to do the unload activities. And so, for example, we wanted to find out the space required for a commercial vehicle load zone in a restaurant district in Seattle. And we knew that the typical truck in this area was a Federal Highway Administration Class 5, which is a 25 by 10 foot truck. Now you need to add another 2.3 feet width so the door can open. And, we noticed that ramps and hand trucks are commonly used for food products. So you need to add another 18.7 feet in the back. And of course, you need another 1 foot on the side so the driver can get down around the side of the truck to get to the back of the truck where they need to unload. And so in this situation, a total load zone envelope is about 44 feet long and 15 feet wide. So there we have some quantitative measurements of kind of what envelope you need to safely unload a truck of, FHWA class 5. You have a bigger truck, you probably need a bigger envelope, or you have different handling equipment, you might need a different size envelope, but you can go to an area, figure out what a characteristic typical truck is, and come up with a commercial vehicle load zone that supports safe load and unload activities. And then we took that data and we passed it along to Oregon State University, and they simulated some of that. So at this point, I'm going to stop sharing and I'm going to pass the talk along to Hisham.
Perfect. Perfect. Okay. Good morning in the West and good afternoon in the East. Thanks, Cole, for the introduction. Thanks, Ed. That was a great presentation. Before I get started, in addition to Dr. David Hurwitz and Dr. Douglas Kolb, I would like to acknowledge Dr. Dylan Horn. Without their efforts, this experiment wouldn't be possible. So thank you all. And by the way, every one of us lives in a different state right now. So yeah, okay, let's get started. So with the knowledge that we gained from other methods that Ed presented, we started coming up with designs for simulator experiment to take a little bit deeper into authentic cyclist responses. Remember that we cannot put them into a real crash scenario. So to do that, we leveraged the human in the loop driving and bicycling simulator at Oregon State University. Now they have the heavy vehicle too, so you may go and visit. So the OSU Bicycling Simulator consists of an urban bicycle placed on the top of an adjustable stationary platform, and that's the bike we're riding, with 10 by 8 feet screen, providing a forward view. The image resolution about 1000 by 800 pixels, which is pretty good. And the sim is surrounded by a sound system to hear the ambient traffic. The computer system that we have right there runs a real-time technology sim creator software. The simulator software can capture and output highly accurate values for performance measures such as speed, position, brake, acceleration, deceleration, etc. Okay. So the experimental design was a factorial one, partially counterbalanced and randomized. And when we think about the variables that were included, we consider the pavement marking by the presence of the loading zone. So here are the examples that we have. So for example, in A shows no loading zone, truck parked in the bike lane. Here we have the minimum loading zone, just the size of the truck. Here in C and D, we have actually the maximum loading zone, size of the vehicle, plus desired operational footprint that Ed talked about. Okay. The second variable is a driver position. So no courier at all, courier behind the vehicle and or on the side. So for example, here we have in A, B, and C, no courier. In D, we have the driver walking beside the truck. And for the example, when the courier is behind the vehicle, this guy right there would be just standing behind the vehicle. Okay. And finally, we thought the presence of accessories might have something to do with the cyclist behavior. So we added that as well. So no accessories at all, or accessories. We add hand track, and we add also some boxes there. So we have in A, B, C, here are the boxes with the hand track. They are small. And here is the scenario when there is no accessories, okay? So as Ed showed us earlier, here the vehicle classifications, and we use the class 5 right there for this experiment. So because we don't have it in the simulator, so I had to build the track from scratch. So that was additional experience I had. And here is the top view that shows the dimension of the road, bike lane, vehicle, and loading zone. So here we have no loading zone. Here we have a minimum loading zone, and here we have a maximum loading zone. I just want to show the top view, but we're gonna see more examples as we go. And here we are showing the width of the bike lane and width of the travel lane as well. And I just put the conversion for you guys. Okay, so when we counterbalance all those variables and variable levels, we randomly seeded each one of those scenarios into a particular location on a testable grid to minimize the carryover effect. We used 5 rideable grids for this particular experiment, and each one with a 3 or 4 exposure. And here is the example of one of those grids. And here are the scenarios that we had 18, because if you recall, we have 3 by 3 by 2, 18 scenarios. We divide them across 5 grids. So we have 3 here, 4 scenarios here, 4 and 4. So here is one of the examples. Cycles will start right here, right past the maximum loading zone, right past the minimum loading zone, and then the no loading zone, which is the truck parked in the bike lane, and then they end their experiment right there. Okay, because we have a civil engineering background, we care about the geometric design. So I started developing the environment from scratch using AutoCAD, Civil 3D, a Blender, and then I use JavaScript to add the dynamic elements such as the driver movement, traffic, etc. And then we come up with the final design and we test it. I always say that for a while, I felt that I have a computer science background. So yeah, not only civil engineering. So into the experiment. So we brought 50 individual subjects into the lab, and we only experienced one case of simulator sickness, which is the one negative outcome that happens when you put folks in the loop simulation environment. Whenever someone experiences simulator sickness, they can become uncomfortable. So we try to identify it as quickly as we can and exclude that data from the data set. Also, 1 is a very, very low rate of simulator sickness compared to other labs around the country. We have a single calibration issue. And so in total, 48 of those subjects generated a full set of usable data, which resulted in about 900 scenarios. Also, So yeah, 864 exactly. If you multiply 48 by 18, you would get that number. Also, we were happy with the demographic variables. So we have very nice split, 25 male and 25 female. And the age range was between 18 and 74. The mean age was 33, about 33. And the outcome variables that we analyzed, or we call them the dependent variable, that we had were lateral position, speed, GSR, and the visual attention. For today's presentation, I will be just talking about the lateral position and the speed. We also had the pre-post survey data to validate the experiment, actually. Okay. So in addition to the demographic variables, we asked participants some other cycling habit questions, just to get insight of their riding experience. These answers could be potential use to predict some of the useful performance measures, such as lateral position or speed. Here are the performance measure variables that we could get from the embedded software. Pretty good software, and we can get many insight out of it. Also, we can plot them. For example, the first one shows the speed right there, and the second one shows the lateral position. So in this scenario, the cyclist deviated from their lane, and at the same time, they increased their speed just to avoid the truck in the bike lane and to avoid the traffic as well. So they were having higher speed, higher divergence from their lane. And this is just an example. We're going to go into the results. So the first performance measure that we analyzed was the lateral position. How much a cyclist would diverge from their lane. A lot's going here, so let's explain what's going on. The y-axis shows the mean of lateral position, where 0 means the center of the bike lane, and about 1 meter, 0.92 meter is the left edge of the bike lane, which is into the travel lane side. The x-axis shows the 3 treatment variables with their levels. So here we have the center. Imagine that you have from here to here is half of your bike lane. Just add this visualization to make it clear. And also here is the travel lane. So by looking at this graph, you will understand that regardless of the career position and accessories, a cyclist diverged the least with a parked truck in the maximum loading zone compared to the minimum and no loading zone scenario. So if you look at this point, we have the least diverge compared to the minimum and the no loading zone. And of course, the opposite with the no loading zone, when the truck parked on the bike lane. So we have the highest diverge, they are actually in the travel lane. And we will see examples. For the career position, when cyclists rode in a scenario that had a career on the driver's side of the truck, the participant actually diverged the highest compared to the other scenarios. So right here, they diverged the highest, but when you compare behind the vehicle, when the driver behind the vehicle, or there is no driver at all, they were, statistically speaking, they were not that different. But when you compare beside the truck versus no driver, they had different actually. Okay, and we didn't see much differences between if there is a hand truck behind the vehicle versus no, and this is a kind of makes sense because it's not obstruct their path. Okay, let's see what's happening from a different view actually. So here is one of the coolest visualization that we came up with. Here's an example that plots plot the lateral position distribution meter on the y-axis, and the x-axis shows travel distance along the bike lane aggregated at each 1 meter. So the dots indicate the data point of each cyclist and their path for all the 48 participants that we had. So in that scenario, the truck was parked at the bike lane without accessories, and the courier was alongside the truck right there. Okay. So we can see here with the parked truck on the bike lane having the highest divergence from the center of the bike lane toward travel lane or the sidewalk. So that was pretty interesting. And this is one of the things that you discover when you design any experiment. I didn't think that cyclists would go use the sidewalk. They will all go they will just go in the travel lane. But actually, when I did the beta test, I saw that some of them, they use the sidewalk. So that's why I had to redesign some elements and do a curb extension for cyclists to make them use that sidewalk. And so we had about 18 cyclists out of 48 decided to take the sidewalk instead of the travel lane. And here, as an example that we have a video, let's see. Here's the cyclist was on the bike lane, decided to take the sidewalk, and then went back. And here they took the travel lane actually. And went back. Okay, for the minimum loading zone, several participants diverge from the bike lane, and this is due to career position. So they try to avoid them. Sorry, but compared to the first case, they didn't diverge earlier or higher. So what I mean by this, if you can see here, they diverge earlier actually, while in this case, they diverge when they saw the driver walking towards them. Okay. So here is a video. So they saw the driver, they actually deviated, they decreased their speed, and then they deviated towards the travel lane. And when we compare the maximum loading zone with others, we can see that cyclists diverge the least, with one case who passed the left edge of the bike lane a bit and went back. And this might be due to the carryover effect, or they were like very cautious about not hitting the driver. And here is another example. And you can see that they were all, most of them, or the majority, they were all in the bike lane. If you compare to these two scenarios, the old ones that you saw. And here's example, cyclists riding their bike. Good, good. And they went through the loading zone. Okay. The other outcome that we had or we tested is the speed. So figure on the top plots the mean speed at y-axis, while each level of the treatment variables on the x-axis. So regardless of the career position and accessories, cyclists tended to have higher speed at the maximum loading zone or the minimum loading zone compared to the no loading zone conditions. While the lowest speed was observed when the carrier walks along the driver's side. What I'm talking about is this point right here. So when the carrier beside the track, they decrease their speed, and because they want to take a decision or they want to be more cautious, or they diverge, so they actually decreases their speed. While here in the maximum loading zone, they were comfortable, they maintained their speed, and they were just going through the loading zone. And here when you have minimum loading zone, and here when you have no loading zone. So the figure below, I will be talking about this green line. The takeaway of this graph shows the two-way interaction between the factors. So on average, the speed of cyclists at the minimum loading zone with the driver on the side were slower than the speed in the maximum loading zone. This indicates that cyclists felt more comfortable riding along the maximum loading zone than having a commercial vehicle parked exactly beside the bike lane, and we have seen that actually. Okay. And here's again for you guys. I will leave my email at the end of the slides. If you have any question about the statistical analysis, I would love to talk about that. We use linear mix effect to do the analysis for both lateral position and the speed. We also ask them some questions, as we mentioned, and here are some questions that participants were asked. So I'm going to read it from the slide. Before this experiment, have you ever rode in a bike lane before that had a commercial vehicle conflicts involved? So that's the first question. We had 80% indicated that they had experienced the conflict before, while 16 stated that they hadn't, and 4 were unsure. For the second question, was related to any obstruction. Similar question, but not necessarily delivery trucks. So we had 45 participants indicated that they had experienced that before, and while 5, they didn't. Again, as mentioned before, to validate our result from the simulator, because it's not a real world, we asked them 2 questions. And here are the 2 questions. Based on your experience avoiding obstruction in the bike lane in the real world, did you make a similar action to avoid the hazard in the simulator? So we wanted to see that. And 87% indicated that they had made similar actions, while 9 only indicated they made different actions, and 4 indicated they were unsure. For the second question, what are your typical responses to avoid obstructions in the bike lane? And take the travel lane had the highest response rate, 29 participants, while 26, they chose right between obstruction and traffic. Interestingly, 19 said that they would use the sidewalk. And in our simulator, we had 18. So it was pretty good validation of process actually. We were happy with that. And this question this question was asked just to validate the GSR. It's not mentioned here in this presentation. It's the galvanic skin response device to measure cyclist level of stress. We are still working on this, but the preliminary results showed that the no loading zone and the carrier on the driver's side generated a higher GSR reading, lower level of comfort compared to others. And the answer to this question kind of approve that and approve what we have seen from the lateral position and speed as well. Okay, so we come up to the conclusion. To sum up, both loading zone size and carrier position had significant effect on cyclist lateral position and velocity. Accessories behind the track had no pronounced effect on both performance measures. The maximum loading zone outperformed the minimum loading zone only when there is a carrier on the driver's side, and we have seen that. And we have 18 out of 48 participants use the sidewalk to avoid the parked truck. So here are the meat of the presentation, the recommendation that we gave. The maximum loading zone size should be used so that it will provide enough buffer for driver to move around the vehicle, and also to prevent the interaction between bicyclists and traffic from travel lane. Barriers could be placed where commercial vehicle exists. The other one is in situation where only minimum loading zone could be designed due to space restriction, the carrier should use the right side instead of the left side. For example, similar to the UBS driver's design, they just go from the right side. We could also increase the width of the bicycle lane when a minimum loading zone is present. This is one of the things that we actually figured out also while designing the experiment. Additional curb ramps could be placed upstream of the commercial vehicle loading zone to allow the bicyclists to transition to the sidewalk if legally permitted. And here is a big debate about that. In a state where allow bicyclists to use the sidewalk, access for the sidewalk should be designed to accommodate cyclists when a delivery truck is anticipated to obstruct the bike lane due to loading and unloading activities. The downside of this recommendation is the potential risk generated from the interaction between cyclists and pedestrians, and we don't want that. The last one, similar can help. Simulator can help, to add precise measurement to design and standard guides as well, and support more effective curb space management and urban freight. So with that, yes, thank you so much. If you have any questions, comments, concerns, we are happy to answer.
Great, thanks Hisham and Ed. That was was a wonderful presentation. Hisham, yep, perfect. So we're going to move into Q&A discussion time. And just to remind everybody, I said this at the beginning, you can type questions into the Q&A box, or if you would like to verbally ask a question, you can hit the raise hand icon at the bottom and we can give you access to speaking. And while you are thinking of your questions, I actually have a few questions. So a few summers ago, I had the opportunity to visit the simulator lab at OSU. That was really fun. And I was one of those people who get sim sickness, so that was unfortunate. One question I had, can you clarify, was there vehicular traffic in the traffic lane that the bicycles were merging into?
Yes, so what we did is we tried to code the traffic that can't interact with the cyclist unless they actually stop and wait for the traffic to come from far distance. And they can hear the traffic that it's coming because of the sound surrounding them. But we didn't actually try to make them interact with the vehicles. We didn't want that because
Okay.
it could be a future study as well to study the crash scenario. Yeah.
Okay. And then Ed, at the beginning, you mentioned that this is one of several projects that this group has been working on together. I guess I have a two-parted question. One, with the results of this work, what does the final product look like? And have you been having conversations with any DOTs about kind of how to use the information that you've come up with in this work?
Yeah, I know, for example, the Seattle DOT, when they found out that we had curve space or, loading zone measurements, they wanted those. So we gave those measurements to them early on. But yeah, so this is almost like a research project, a program, because we initially started looking at bikes in urban areas. And we realized that bikes are pretty much perturbed by loading and load activities. So that's kind of where we led to this NICS project. And so we're looking at bicycles, but we now have a brand new PacTrans project where we're going to look at from the driver's perspective, because they have a driving simulator in, at the OSU lab. So we can look at bicyclists and drivers, how they react to commercial vehicle load zone. So we're going to get kind of all these elements and hopefully design a good commercial vehicle load zone. And our ultimate goal is to have some sort of standard, just like a handicap zone, where a planner and engineer in some city says, hey, there's a huge amount of e-commerce in my city. That condo with 60 units is sure generating a lot of traffic. I need to put in a commercial vehicle load zone, but how do I design one so it doesn't get in the way of the bicyclists and the pedestrians in this city? So, hey, here's some data, and that's kind of our ultimate goal. So we want design standards, and I've presented this information in Europe where they have a little bit different perspective, and they were really interested in the measurements because they also have pretty crowded curb space. So, yeah.
Great, thank you. Okay, so we do have a few questions rolling in, so I'll get to these now. At the state and local government level, what practices or guides can help government officials better plan for commercial loading needs? Is there anything fleets can do to ease urban delivery, such as change door locations on fleet trucks or dispatch drivers at certain times of the day?
I'll start, and maybe Hisham could take it. We think that maybe doors on the side of trucks have some of the benefits as long as you're not parking in front of a light pole. I think that different, delivery companies kind of need to right size the truck for the urban environment, and some places ramps don't work. So it's kind of a private sector decision, but I think the cities can kind of be aware of the fact that these trucks probably need more space than they think they do, and use data like that. And then let's see, the other question was, about different times of day. Yeah, everybody says, let's have trucks deliver in the middle of the night. The problem is, if you're a small business, and you have 3 employees, you don't want to pay one of your employees to be there in the middle of the night to accept your goods. And if you're delivering alcohol, you can't deliver it in the middle of the night. And Yeah, so the delivery companies deliver when the customers not want the goods, not when it's convenient for traffic. So
I think you crushed it. Yeah.
okay.
Great. Let's see. And then we have, thank you for the great presentation. What about areas where there's no opportunity for any kind of a redesign? If there is a one-way street and the only place for the truck to park is in the travel lane or in a bike lane, where should they park? Based on what you saw in your experiments, does it make more sense for cyclists to move into the travel lane, or is it better to have cars drive into the bike lane when traveling around a parked truck?
So we have a system that is forcing drivers to do their job and break the law, right? So that something doesn't seem right about that. I know in New York City, like UPS just automatically pays the city of Seattle millions of dollars for the fines they're going to get because they know they're going to park in the turn lanes and things like that. I think there's other things you can do too. You can put lockers in. Maybe so the trucks can deliver to lockers. You have load zones from lockers. People come to the locker to get their goods. Maybe you have more dynamic curb zones where, in the morning it's people, in the middle of the day it's good, in the evening it's Uber and Lyft. I mean, there's things you can do so you don't force trucks to block traffic, but that's also going to happen because it's just the way they do the job. They have to do the job. And curb space is getting more and more scarce as more and more of us order things online. And there's, once COVID's over, more and more of us will probably keep using Uber and Lyft. The thing about Uber and Lyft is if you try and drive your car downtown, you can't find a place to park. Next time you're more likely to use Uber and Lyft, and then that sort of a cycle there, and there's more and more Uber Lyft, more and more demand for curb space. So it's a problem that's not going to go away, which is, as researchers, that's why we're looking at it.
Yeah, we can test every scenario in the simulator, but it has to be like legal first, and second, yeah, I mean, it would be a great opportunity for future research to see the interaction between the cars and the cyclists, actually. So we can bring two subjects that they can drive and they can bike, and we have this option in our simulator right now.
Yeah.
Does your simulator, sorry, just to piggyback on that, does your simulator have the ability to have someone in a vehicle and someone on a bike in the same setting simultaneously?
Yep, and in the truck as well. So we have developed that.
Interesting. Okay.
Yep.
Great. Next questions. Thanks for the great work. Curb space management is a new topic emerging recently with the quick growth of e-commerce and TNC services, as you mentioned a few times, Ed. I wonder what you see as the key issues that deserve theoretical research to improve curb space management.
Figuring out new solutions. I mean, curb space is a limited commodity. So there's a whole bunch of things you can do. You can look at, hidden freight infrastructure, like loading docks in buildings that are in private buildings. Maybe you open those up to people. You could put micro hubs in, and maybe you have big trucks go to a parking lot and it distributes to a cargo bike, and the cargo bike does delivery, or the driver walks out and does deliveries. I already mentioned lockers. Maybe right now curb space, the technology is a paint stripe. Maybe you have dynamic curb spaces that change color depending on who can park there. I mean, this is a kind of a new field, and I think there's a lot of possible, we just need to look at some innovative ideas. And of course, you want to make sure the commercial vehicle load zones, when you do install them, work safely and they're the right size, so they're actually useful, right? If you have a curb space that's just 2 feet too small for a typical truck, a load zone, that's wasted. You make it 2 feet longer, it's more useful. So that's there's a lot of research possibilities there.
Yeah, that could be a great competition for students actually to come up with a new design. Traffic control devices, we have to contact them from TRB for that. Yeah.
Another thing you could do is you could probably use technology and come up, like we're working on a project where you have an app that kind of predicts when a commercial vehicle load zone might open up based on past history and sensors. Well, that's another way you could do. You could reserve spots or just predict spots that would open up for the trucks.
Great. to our audience, does anyone else have any questions for our presenters today? Okay, well, in that case, we can end a few minutes early. First off, I would like to thank you to both, again, Ed and Hisham, for not only the hard work, but taking the time to share it with us. To the audience, we have recorded this session. We will put it on the PacTrans YouTube channel, and we will distribute it via our website and newsletter as well. So if you'd like to go back and revisit or share it with others, we have that. And then the last thing I will say is we've got a lot more PacTrans webinars, series webinars in the pipeline right now. So stay connected with us for future opportunities. We're also in the preparation stage of launching a PhD student webinar for our region, where it's basically student-led and student-run, and they have an opportunity to present their personal research work, which we're pretty excited about. So that's coming soon. And if you would like to get in touch with Hisham or Ed with any lingering questions or to see more about it, please feel free to email any of us, and we'll make sure to get you connected. So thank you, everyone, and have a great rest of your morning or afternoon, depending on where you're joining us from.